Okay, so this is another question from another exam about nuclear physics and beta decay and alpha decay. So the question is about a uranium isotope. So there's uranium-238, which means that this uranium atom has 92 protons, and in total it has 238 protons and neutrons together in its nucleus. So you have protons, or drawn as these black dots, and neutrons. And this uranium atom is a bit unstable, so it might decay into another atom, and then that atom might decay as well. And then after a series of decays, this uranium atom might decay into a lead atom, Pb, which stands for plumbum, which is the Latin word for lead, which has 206 protons and protons and neutrons together in its nucleus, and it has 82 protons. And then the question is, how does it exactly decay from this uranium thing into this from this uranium atom into this lead atom? And there are various ways by which this decay process can occur. One way that these atoms decay is by alpha decay, which means that a chunk of protons and neutrons, 2 protons and 2 neutrons actually, will sort of break off from this atomic nucleus. So that is actually exactly how a helium atom looks like. So there will be 2 protons and 2 neutrons, so there will be 4 nucleons in total that can sort of break off, and that is called alpha decay. Another way that this decay can happen is by beta decay, which is, this can be beta plus or minus. And what happens in that case is that one of the protons basically changes into a neutron, and if it changes into a neutron, then it will emit a positron particle. It can also go the other way, that a neutron will decay into a proton, then it will emit an electron. And now the question is, this uranium decays eventually into this lead, and given in this question is that this decay process happens by means of 8 alpha decay. I think 8 alpha decays. Yeah, alpha decay is okay. So in a series of decays, alpha decay occurs 8 times. And beta minus decay, which is the one where the neutron goes to a positron and then emits an electron. So this process occurs n times. Alpha decay occurs 8 times. 8 times alpha decay, and n times this beta minus decay. And the question is, how many times does this beta minus decay have to occur after alpha decay, if alpha decay occurs 8 times, to go from this uranium atom into this lead atom? Now, how you can calculate that, or how you can see that, is that you know that every time alpha decay occurs, 4 of these nucleons sort of separate from this atomic nucleus. So 2 protons will be lost and 2 neutrons will be lost. So if that would happen 8 times, then the particle that you would get after 8 times alpha decay would be something, I don't really know the name of it, that has 206 protons and neutrons in total, because you know that 8 times 4 is 32 of these have been lost. So 206 will be remaining. And in addition to that, there will be 76 protons in the nucleus. And then the question is, if this thing now has to go into a lead particle, you know that it will need to gain 82 more protons in its nucleus. So, because when beta minus decay occurs, a neutron will be turned into a proton. So this number here of total nucleons will stay the same, but a neutron will be turned into a proton. And you need 6 more protons. You know that 6 times, so this n here, 6 times beta minus decay has to occur to get eventually into the lead particle that we were interested in. Okay, so for the next question, or next part of the question, we needed this graph, because this is given to you when you make the exam. And this graph tells you for different atoms with a different total number of nucleons, what the binding energy of that nucleus is going to be. So 238, so this is the binding energy on average per nucleon. So if you would average it out over, so for example, uranium has 238 nucleons, so that would be somewhere over here in this graph. And you see that it on average has 7.6 mega electron volts per nucleon in the binding energy, that is the energy that sort of keeps all these particles together in the nucleus. And then the question is, use this figure to estimate the binding energy, the total binding energy, in mega electron volts of this lead atom. So we know that for lead there are 206 nucleons, so that would be somewhere here in this graph, around 205. So then you see that there is 7.9 mega electron volts on average for each of these nucleons. So to estimate from this graph the total binding energy of the lead nucleus, you can simply multiply the 206, which is the number of the nucleons, times, let's say, 7.85 mega electron volts. You can keep the answer in mega electron volts in this question, because that's what they ask you for. They calculate it in mega electron volts, they say. So if you, and then you'll find that the total binding energy of this nucleus, the calculation that earlier I had a 9 here, which is a minor detail. So if you would have a 9 here, so it would be 7.89, you can maybe say 7.8, 85 is a bit less, 89 is maybe better. So then you would get 1625.34 mega electron volts. And you don't have to, for this particular question, you don't have to have one exact answer. There's like a range. If you sort of had the right, let's say everything above 7.88 or something is sort of going to give you an answer in the range that they will approve. So you don't have to worry too much about exactly estimating the right energy. It's more about understanding the method of how you have to do this. So then the next question is about the half-life of these uranium atoms. Because these uranium atoms, they are unstable. So imagine that you have a rock of freshly formed uranium atoms, then over time they're slowly going to decay into lead atoms. And the half-life of uranium, I'll write that down here, half-life, is 4.5 times 10 to the 9th years. Which means that if you wait 4.5 times 10 to the 9 years, half of the uranium atoms in that rock will have decayed into lead. So if you now have a rock that, when it is formed, contains 3 times 10 to the 22 atoms, so this is 3, and everything here is sort of the number of atoms times 10 to the 22. Is it readable? Should I write it a bit bigger?
Nice.
Alright. So 3 times 10 to the 22. So you start with a rock that has 3 times 10 to the 22 atoms, and then it will slowly start to decay over time. So you know that after 4.5 years, you only have 1.5 times 10 to the 22 atoms left. And then after, so this is 4.5, and after 9 times 10 to the 9 years, you only have 0.75 of them left. 0.75, and this is going to be 1.5. And then the question is, draw a graph that shows you the number of uranium atoms and the number of lead atoms in this rock as a function of time. So for the number of uranium atoms, it is a bit straightforward. It's what I just told you. You start out with 3 times 10 to the 22, and it sort of halves every 4.5 times 10 to the 9 years. So you get a graph that looks like this exponential decay that sort of goes like this. And the number of lead atoms is, of course, the number of uranium atoms that have been decayed, because they will turn into lead atoms. Because, of course, it has this complicated decay process, but all those intermediate steps are rather unstable, and they say in this question that you can neglect whatever happens here in between. So you can assume that everything is either uranium atoms, and whatever one of those things decays, it directly turns into a lead atom. So you start out with 0 lead atoms, and after 4.5 billion years, is this right? So 4.5 billion years, when half of your uranium atoms have decayed, you gained that same number in lead atoms. So this is the number of uranium atoms. And then when I have only 0.75 uranium atoms left, I have 3 minus 0.75, which is 2.25, somewhere over here, is the number of lead atoms that I have. It's going to be an ugly graph. So, and this will asymptotically go to 3, whereas this here will go asymptotically to 0. So this is the number of lead atoms. So this is question C. Draw this graph.